$8,000. That was the approximate price of communication for thousands of people around the world. This summer, I got to volunteer at Camp, which helps people with disabilities to enjoy and experience summer camp like anybody else. In our training guide, they went over how valuable eye-to-speech devices are, which many people use to communicate when they are unable to speak and are paralyzed, and how, at times, they are the only method of communication for some. These devices can range from 10 to 15,000, pricing out lower income families who may be unable to afford communication in case these devices are lost. We wanted to provide an alternative solution so no one could be priced out of communication. SpeakEasy's language generation model engine is powered by a quantized GPT-2 model that fully runs on device. By compressing model weight to 8-bit precision and optimizing layer-by-layer scaling, the system drastically reduces memory usage while keeping prediction quality nearly identical to the original transformer. The model runs in a continuous next prediction loop, caching previous attempted states so it doesn't need to reprocess all tokens. This cuts computation time and keeps latency below 200 milliseconds per prediction. A lightweight tokenizer and contact manager handle input text dynamically, feeding it through a top K probability sampler that selects the most likely next word in real time. This creates a next word suggestion model using GPT-2.
For the system architecture, we use a client server. A Python fast API backend processes WebSocket video at 10 frames per second. A React Native frontend handles UI and camera capture. Fast API exposes two channels, REST endpoints for health checks, calibration storage, and GPT-2 text predictions, and a WebSocket that streams frames upstream at 10 frames per second and returns gaze data in real time. We publish through Cloudflare tunnels to secure HTTPS/WebSocket with an automatic TLS. The gaze tracking pipeline runs 5 stages. 1. MediaPipe Face Mesh, a convolutional neural network, detects 468 facial landmarks, including iris key points. 2. We extract iris landmarks and compute the centroid for iris localization. 3. An eye aspect ratio over 6 eye landmarks detects links. 4. Calibration users fixate on directional targets. It transforms mapping iris coordinates to screen coordinates and improves accuracy. 5. A hysteresis-based state machine classifies offsets into discrete directions with an enter threshold to prevent oscillation.
Hello everyone.
The front end is built with React Native plus TypeScript for cross-platform compatibility. Using Expo's camera API, we capture 720p video. Each frame is JPEG compressed at quality 0.3 reduced bandwidth, and then sent as binary WebSocket frames to the backend. Navigation is grid-based, and a 180 millisecond debounce prevents accidental moves. A centered gaze increments a dwell timer every 50 milliseconds and triggers selection at 5 seconds, with a progress bar updating every 50 milliseconds. Text-to-speech uses Expo speech APIs with platform-native engines.
As we can see, not only does SpeakEasy create efficient and affordable eye-to-speech devices, but creates leaps and bounds for accessibility and communication for all.